Welcome back to Honors Calculus. In this video, we are going to continue our discussion of differentials with the idea of the title, namely differential form. As we've seen in our discussion on implicit differentiation and related rates, very often we run into a bit of a problem in this form of not always being clear what variable a function is in order to take a derivative. If we have a v and a v prime and an r prime, what are we taking the derivative with respect to in r prime and in v prime? The obvious way of solving that is just putting explicitly of values. V of t, r of t, r prime of t everywhere in the problem, which absolutely does work, not a problem. But there's another option which is not always entirely clear why it's useful, but is going to be useful to us moving forward. That option is called differential form. So if we have y equals f of x, we have so far said that, getting ahead of myself, y prime is f prime of x, or if we wanted to be specific that we were performing a derivative, d over dx of y is equal to f of x. Now, d over dx is not a fraction, but it kind of looks like a fraction. So the whole idea of differential form is, what if we decide to completely throw away all the rules of math and just pretend that this thing is a fraction anyway? And even though it is not multiplication, let's pretend that we're multiplying anyway. And d over dx times y would be dy over dx. Then, again, not a fraction, no reason we should be able to do this, but it kind of looks like a fraction that has dx in the denominator. So what if we just multiply both sides of the equation by dx, and we write that dy is f prime of x dx. This gives us a different way of writing out the process of implicit differentiation. When you take the derivative of y, we'll call that dy. When you take the derivative of f, because f is a function of x, we'll call it f prime, and then we'll tack on dx, the derivative of x, the rate at which x is changing. And when we are doing implicit differentiation, we can use this process or this notation to do the same processes we had done before. Right? So if I have something like x squared over 12 plus y squared over 15 is equal to 1, and I take the derivative of both sides of this, the derivative of x squared is 2x. And then I throw in a dx because I'm differentiating with respect to x. The derivative of y squared is 2y. And then I throw in a dy because I'm differentiating with respect to y. And I can do some rearranging. And I can divide by 2y over 15, and I can also divide by dx to get that dy over dx is 15 over 2y times 2x over 12. And all of the reducing we can do on that, I get that dy over dx is 5x over 4y. So this new notation doesn't seem to have done much of anything for us. But it exists and it works, and that's kind of the only thing that matters right now. This other form is also, generally speaking, considered to be the better form for another application of implicit differentiation, and that application is the propagation of error. If I'm looking at something fairly straightforward, the volume of a box. Now, in order to calculate the volume of a box, I must measure the length of the box, the width of the box, and the height of the box. So far, in any mathematics course that you have studied, you have assumed that measurements are exact. And so far in this course even, we have almost always looked at calculations as though we had exact values for everything. But in reality, that's not possible. Our measurement equipment has limitations. For example, if I get a meter stick out, my meter stick is marked to the nearest millimeter. If I have a difference of less than a millimeter, my meter stick cannot interpret it. So if I measure this box and I get that the length is 36 centimeters, and I get that the width is 25.2 centimeters, and I get that the height is 47.5 centimeters. Well, my meter stick is plus or minus 1 millimeter, 1/10 of a centimeter. So these measurements are all plus or minus 0.1 centimeters, plus or minus 0.1 centimeters, plus or minus 0.1 centimeters. How do we determine the error in the volume calculation based on all of those little errors that add up? It's not going to be a lot of error, but we should be able to quantify it based on how accurately we measured the length, the width, and the height of the box. How accurately can we state the volume of the box? Well, we know that volume is length times width times height, and we can calculate the volume. If we declare that the error in the volume is dV, the error in the length is dL, error in the width is dW, error in height is dH, we can also figure that out by differentiating implicitly. Again, I'm not using V prime and L prime because it's not really fair to say that V is changing with respect to time or with respect to something else. We're looking for how far off we are. So that's why we use the notation of dV. On the right-hand side, we'll need to use the product rule. The derivative of L is dL times W times H. And then we take the derivative of W, L times dW times H. And then we take length times width times the error on H, which is dH. By calculating this, we can figure out how accurately we know the volume when we plug these numbers in. So knowing my numbers, my volume itself will be 36 times 25.2 times 47.5. And my calculator is quite happy to tell me that when I punch all of that stuff in, I get 43,092 cubic centimeters. Now in the differential, I've got a bit more of a mess going on, but that's okay. It's still just a matter of plugging stuff in. DL is 0.1, W is 25.2, and H is 47.5, plus L is 36, DW is 0.1, and H is 47.5. It's very convenient doing this calculation when all of the errors are the same. And then for the third term, L is 36, W is 25.2, and DH is 0.1. So when I plug that into my calculator, I get 381.42. So my volume is 43,000 and change, plus or minus 300 and change. Very often we round to one significant digit, we say. Plus or minus 381.42 is correct, but really plus or minus 400 gets the job done and is easier to work with. But we see that this error, 1 millimeter off either way, because that's all the better our meter stick is capable of, gives us a total error of nearly 400 cubic centimeters in the volume of this box. Now, 400 cubic centimeters is not a lot when you're looking at a 43,000 cubic centimeter box, but it's still more than you might have expected at first glance. Here's a similar problem for you to take a look at. Let's imagine a right circular cone. And once again, we're going to be looking at the area of this thing. So we have a right circular cone here. And I measure the diameter, the distance all the way across the cone at 12.8 plus or minus 0.2 centimeters. And I measure the height of the cone as 14.4 plus or minus 0.2 centimeters. Now remember that the volume of a cone is 1/3 pi r squared h. I would like you to use implicit differentiation and the differential notation to calculate the error in this measurement of the volume of the cone. Take a few minutes, see what you can do with that problem, and I'll see you in the next video.